transfer function and stability of the systems. So first of all, transfer function nothing but is a ratio of the Laplace transformation of the output to the Laplace transform of the input. So here we should take all the initial conditions to be 0. And if you are taking the u of t for plant, u of t is u of s, and here the Laplace transform of the y of t is equal to y of s, and we release the Laplace operator. And the transfer function of the any plant should be written as g of s is equal to v of s, y of s by u of s. So here u of s is the input to the system and y of s is the output to the system. So here why we should consider the Laplace transform. Using the Laplace transform, we can convert many common functions into algebraic function of the complex variable. So for example, Laplace transform of sine omega t is equal to omega s square plus omega square. And similarly for Laplace transform of exponential equation, for example, if you take the e power minus at is equal to 1 by se, and we can also write this Laplace transformation in s domain, that is s is equal to sigma plus j omega. So here we are called as this is the complex conjugate of the function. And if you are taking the Laplace transform of derivatives, and not only the common function can be converted into simple algebraic expressions, but calculus operations can also be converted into algebraic expressions. So for example, Laplace transformation of dx of t by dt is equal to s into x of s minus x naught j. And similarly for Laplace transformation of derivatives in general, we can written as Laplace transform equation of d power n x of t by dt power, where x naught is the initial conditions of the system. And next, coming to the Laplace transformation of integrals. If you are taking the Laplace transformation of x of t into dt is equal to 1 by s into x of s. So in time domain, integral becomes division by the s in the frequency domain. And for the calculation of this transfer function, so here I am taking the y of t is the input of the system and x of t is the output of the system. So for this system, if you are writing the Laplace, apply the Laplace transform to both sides, we will get this final equation. And here we are considering all the initial conditions to 0 in order to find the transfer function of the system. So finally you get the equation x of s by y of s is equal to cs by as square plus bs. That should be written as c by as plus b. So this is the general transfer equation of the any system, where x is the input to the system and y is the output of the system. So from this we can write the transfer function g of s is equal to Laplace transformation of the output by Laplace transformation of the input. So here we are considering the 0 initial conditions. Then we will get the y of s by x of s. And here always the n should be greater than or equal to m. When order of the denominator polynomial is greater than the numerator polynomial, the transfer function is said to be proper transfer function, otherwise it should be improper. And mainly the transfer function can be used to check the stability of the system, time domain and frequency domain characteristics of the system, the response of the system for any given input. And there are several meanings of the stability. In general, these are two kinds of stability definitions in control system study: absolute stability, relative stability. And we can express the stability of the control system like p of s by x of s. Roots of denominator polynomial of transfer function are called poles, and the roots of the numerator polynomial of the transfer function are called zeros. And the poles of the system are represented by the x, and zeros of the system are represented by the o. The system order is always equal to the number of poles of the transfer function. And here the following transfer function represents the nth order point, that is for any physical object y of s by x of s. And poles is also defined as it is a frequency at which the system becomes infinite, hence the name pole. where field is infinite. Zero is the frequency at which the system becomes zero. And poles is also defined as it is the frequency at which the system becomes infinite, like a magnetic pole or a black hole. So we can represent it as y of s by x of s. So for example, transfer function can be calculated as g of s is equal to x of s by y of s. Here I am taking a c by as plus b. The denominator polynomial is as plus b is equal to 0. So for this only the pole of the system is s is equal to minus b by a. So like that, for the given transfer functions we have to find out whether the transfer function is proper or improper on poles of the system, zero of the system, order of the system. So like that we can convert the transfer functions into the poles and zeros to transfer function. Thank you for listening.